Welcome back. Today is February the 4th, and we're going to continue solving unknowns for NMR. All right? And last time when we met here, I solved for this particular case. All right. So just like you see here, just like you see in this picture right here, that's what I'm expecting from you to solve for these unknowns. All right? There's a little bit of confusion of what is expected and what is what. So I'm going to go to Canvas just to clarify things. The package that I'm showing you as practice, I used to do it in a lab. That's why it says lab, but ignore that. Whatever is on this class is practice homework. It's not lab. I didn't have time to like edit that. But then you have two packets. You have these packets here, A through E. That's what I'm expecting you to do next week. And we'll have a quiz this coming Tuesday on NMR. And then I don't have a practice pack for the mass spec, so I'm going to grab A and solve it in class with you guys. And then you do B, C, and D. I'm gonna check for completion, and I'm gonna give you the 20 points, whether you have it right or wrong. But I want to see effort. I don't want to see like like a little bit here and like I just recognize a carbonyl and that's it, on the infrared. No, I want to see effort. I want to see that you do write stuff down there, So that's what I'm looking for. Okay, because this is going to be extensive if I'm going to grade. I'm going to grade the quiz really carefully so you can see what I'm expecting on the milestone. But for homework, I'm just going to look for completion.
You will give those back to us, right? The quizzes and stuff.
Yes, if I don't get the quiz back to you, I will post the key at least so that you can see what I'm expecting. All right? Because for the mass spec quiz, I probably won't have time to, unless you stop by my office. I can give it to you, but that's like on a review day, and then the quiz is the exam is the next Thursday, so it might be rough. Yes.
So when do you want all the packets completed?
Yeah. So this one. So I said like the NMR. The NMR package is due on the 11th of February, like a week from today. And then next week we'll start GCMS. I mean, not GCMS, MS, mass spec. And then I want that due on the 18th, but that's like the day of our milestone, our milestone 6. Yes, ma'am.
So for the lab schedule, it says that the mass spec is due in lab. Is that a different mass spec package?
No, see, yeah, that's a different package. I'm just going to show you that. Yeah, I'm going to show you that. So basically, this week, all you got to do is solve NMR for the lab and for my class. Yes, sir.
Is there a section on it? I know Pearson just got started. Is there a Pearson section on this too?
Not yet, not yet.
So there's nothing to do with Pearson?
No, nothing to do with Pearson until we get to, let's see, where's the class schedule? Right here. So, for the class schedule, notice that we're doing infrared, NMR, and mass spec. All of this will be combined here and finished by February the 18th. By the time we get on February the 15th, we should be rolling with the electronic Pearson online homework. All right? So start setting it up for now. I linked one of the two courses that I have, but the same thing, but one I cannot link it. And then I have like several students registered. But if you register and you just transfer to the other one, it will be fine because I don't have anything assigned yet there. So we'll be starting off clean. All right. So Jesse, so the question for you is now you understand what's due for this class, right?
What's confusing me is on the mass spec packet, it says like lab week 1A.
Yeah.
Is that the one that's due for your class or the one that's due for lab?
Well, let me show you. So that's what I'm saying. Like this used to be a lab for me. And I built this for my lab, just like the one you're doing for the other lab, for this university. So like when you see, and it says here, lab pack, yes, I used to do this as a dry lab. And that's what I'm saying, ignore this here. It should just be called Pack A, mass spectroscopy, because it's in class now for a lecture. But then, for your labs, so let's say you're on the Tuesday 140 lab, for example. This is what is due there. This week, you also have to solve right here. This practice packet, we started it in the lab this Tuesday, this past Tuesday. And then you have to solve, for this, you have to solve these 3 unknowns. You have 3 unknowns due for the lab. All right? These are really labs ones. Actually, these ones don't say lab, they just say unknown. It's opposite. But yeah, these are the 3 unknowns for the lab. All right? And those are due next week. And the next week, we also do the mass spec, splitting the times like we did last time. So arrive at the same time. Okay? Is that clear? All right. Yes.
Do we have to turn in the 45-page example thing too that we started in the lab? The practice?
I want to see it. You don't need to turn it in, but I want to see it. Bring it. Because I don't want to collect it and I'm not going to do anything with it. I just want to see that you're practicing. And I said that in class. I think I said that in the lab. If you're not practicing it, you're hindering yourself any chances of success. Because the more you try, the better you get at this. By the time you do the quiz next week, that's about what I'm going to expect from you, like solve one whole unknown in 15 minutes. And I like to do my quizzes in class at the end of the period. A lot of students don't like that, but at the end, you will see that you would prefer that because there's a seamless transition. You come in, turn it in, and leave. Turn in and leave. Quietly. People leaves. The other thing is like, if you need 5 more extra minutes, I'll give it to you. You know, all I need is 5 minutes to run to the lab. So you get an extra 5 more minutes. So that's a good thing. But then you have less 5 less minutes to go to your next class. So choose your poison, right? So that's how that goes. So, but I always try to give you an advantage. So when you come here, do not think about the quiz. Think about, relax, take a look at the lecture, put your mind at ease, and when it's time for the quiz, you worry about that then, okay? Because a lot of students, they want to get that quiz done. You know, it's like, that is old school. You know, I'm not old school at all. So I like to like innovate. And I think it has worked for me for many years. And I think at the end, you're going to prefer that. It might just be a culture shock for you for a second at the beginning, but that's not bad. All right. Let's get any more questions about homeworks, quizzes, and assignments. Pearson. All right. I hope it's clear. Okay. But if it's still unclear, let me know. All right. I don't mind you asking me 10 times the same thing. All right. All right. All right. So I'm going to close this and we're going to start. And we're going to do unknown number 34 now. All right. So I'm going to check unknown number 34. Where is the other page? Oh, right here. I'm going to look for the formula. This is what I do. I just group all this. And honestly, I don't have a key for this thing done. I'm going to have to grade you and see what you did or do it by myself again. But I've done it so many times that I wish I would have saved a key. But it's fun. It's okay. So we are on... I'm going to do unknown number 34 right here. Where's my draw? Oh, yeah. So right here, we're going to be doing this one. All right? Okay, so let's go over here, and I'm gonna start. And by the way, this is being recorded, so if you're not here, you can still watch this later when you hear this recording. All right, so, let me see what the structure, molecular formula was. So that's C4H10O. I have C4H10O. All right, I'm going to calculate. Number one thing I'm going to do, find the DUs. So DU will be equals to 2 times 4 plus 2, because I don't have a nitrogen, minus 10, divide all that by 2. I get 2 times 4 is 8 plus 2 is 10, 10 minus 10 is 0. All right, so I'm okay here. I don't have any degrees of unsaturation. All right. So, and I don't memorize this spectra, so they're blank. I don't even have a key, so I like to solve them every year just to keep my mind sharp. So 1, 2, 3. So the next thing I'm going to do is find my type of carbons. So I have 3 types of unique carbons. All right, so the moment I see 3, and then I check my molecular formula, and I see that I have 4 carbons here. That means 2 of them are equivalent. So they might be mirror images when you cut through a plane of symmetry, all right? So that raises a flag immediately. All right. The third thing I'm going to solve is my infrared. All right. I see this nice round, soft U-shaped band, and I know that this is an OH group. All right. If this is an OH group, I must have a CO stretch, because each alcohol has an oxygen that is being held in on a carbon. All right. And then, yes, let me see. I don't know what this peak is, so I'm gonna leave it. The long one that is there, I cannot solve for that. All right, but I can solve for the 3000 line, the magic line. I'm gonna trace it up, right? And I know that there's nothing on the left side. Everything on the left side is sp2CHs. Everything on the right side is sp3CHs. So I was able to assign 3 bands. That's not bad. So then I'm going to move on with the proton NMR. I'm going to first, before I do anything, I'm going to label all these peaks with the alphabet letters A through C from left to right, so that everybody is the same. All right? So when I'm grading, that should make my life easier too. I don't care how you drew it on the structure and you assign them on the structure, but from here, I need to see A through Z from left to right, okay? And that's just to be organized. So I'm going to go A, B, C, and D, and I'm good there. All right, you see that? So when I finish the structure, if the structure is flipped to the right or to the left or upside down, I'm going to be able to grade your progress and see, oh, that's A, that's B, that's C. Then, you see what I'm saying? But here on the spectrum, it's good to get it right. All right. So what do I see here? I see a singlet that integrates for 1H. What do you think that signal is based on your infrared? The OH is by itself. The electrons on the oxygen block any splitting from the OH, from the H towards any carbons that have hydrogens. Therefore, that's an isolated signal. So I'm going to assign this as an OH, and because I have an oxygen there on my formula, I have to assign that oxygen. I'll get rid of it right away. Then I look at the next signal. The next signal is it's integrating for two H's. So what is that? CH2. It must be a CH2. So I have what I like to do is I'm going to write it down and put it in a box. That's just my style. You can come up with something else. But then that tells me that that's my peak of interest. And then outside that box, I'm going to connect it to its neighbors. So how many neighbors does he have? One neighbor. So this is going to be connected to something that is here, that is blocking having a neighbor, and is connected to a CH. How cool is that? That is the only combination you have for that signal. Do you see that? It's a CH2, so it needs two bonds. And only has one neighbor, so one has to be a CH, and the other one has to be something that doesn't have neighbors, like the OH, right? Okay, then I'm going to look at the next signal. I have 9 peaks. For any milestone that I'll give you, if I know that you might not recognize these little things as peaks, I will tell you that you need to count them. So we're going to count those, okay? Because they're so tiny, they almost look like grass or NMR grass. 1, 2, 3, 4, 5, 6, 7, 8, 9. We had 9 peaks. Perfect. All right? So 9 peaks means what? How many neighbors do you have? 8. So there's only one combination to have 8 neighbors. And it's this one. You have your signal of interest, which is what? How many hydrogens are in that signal? It's a CH. There's one. So you have a CH, and then that's going to be connected to CH3, CH3, and a CH2. That's a total of 8 neighbors plus 1, that's 9. And then this guy is going to be connected to something, but we're going to leave it there. All right, and finally, I didn't block the oxygen. Let me block it so that we have, it's uniform. Then you have this doublet that integrates for 6 hydrogens. What does the integration of 6 tells you? 2 CH3s. So this is going to be equals to 2 times CH3s. And how many neighbors does each CH3 have? So you have 2 CH3s connected to how many neighbors? 1. They'll both be connected to a CH. All right. So now I'm going to solve for this. I'm going to grab all of my boxes. I'm going to put them together. So basically you get these boxes. You say OH. Well, let me put the H on the other side. OH is attached now to that will be a CH2 that is attached. So that will be signal B, and then that's attached to a CH that is attached to 2 CH3s, right? And we solve for that. Now, I like linear structures, so you can do it like this. But for simplicity, you go OH and you go 1, 2, and then 1, 2. That's better. All right. So then you label this again based on the labelings that you have on your spectrum. And then this will be signal A. B is a CH2. C is that no-net. So there's 9 peaks, so it's a no-net. And then D will be your 2 methyl groups. 1 here and 1 here, and we're good. All right. we're going to now calculate the shifts for A, B, C, and D. All right? And then we'll say, okay, what is A? Based on this chart, A is between 2 and 5. Chart number. So this would be 2 to 5 ppm. It's showing up around 4, 3.9 to be exact. Chart. We'll call it singlet. It's not broad enough to call it broad singlet. That's a singlet that integrates for 1 hydrogen. All right. Now B. B is a doublet. Okay. So what is B? B is a CH2 attached to an oxygen. What is the signal for that?
3.3 plus 0.2.
Exactly. 3.3 plus 0.3 because it's a CH2. 3.3 plus 0.3 because it's a CH2. Do we have a beta group there? No. It's out, there's an alpha group to it, but that's not a beta. That's equal to 3.6 ppms. It's a doublet that integrates for 2 hydrogens. That's a CH2. All right, check it out here. So here the signal is roughly 3.4, so that's good. We're close. Plus or minus 5.5 in this case. So we're within range. C is the non-net. Notice that here will be really hard to see what that was. Like 1, 2, 3, 4, 5, 6, 7. And there's 2 more that were lost. So that's why these inserts are great, because you can really see them being blown up. All right. I'm going to delete all this. All right. So C is a CH. It starts where? Here in the chart. Anybody? 0.9, yes, because the C is connected to B, which is another C. So that'll be excellent. 0.9 plus what? 0.7 exactly, because it's a CH. Does he have a beta group? Yes. So we add 0.3 because he has a beta group. So that's a total of 1.9, right? Yes. 1.9 ppms with delta. It's a non-net. You could also say multiplet, but if you can count the peaks, it's better to say the right splitting. In this case, it's 9, so non-net that integrates for 1 hydrogen. All right. Finally, D will be 0.9 because it's a CH3 attached to a carbon. Right? This is a CH3 attached to a carbon. And then that's going to be a chart value because it's already a CH3 and it doesn't have a beta group. It has a alpha, beta, gamma, so it doesn't count. So it's too far away. So this would be chart value, and it's a doublet. And then it integrates for 3 hydrogens. All right, what is the name of this molecule? Name. 2-methyl-propan-1-ol. Very good. So let's label those carbons to remind you. You have 1, 2, 3. So it will be 2-methyl propan 1-ol. All right. Questions like this. I want you to, for the quiz, same thing. So for the quiz, maybe I'll give you like how many types of carbons, and I'll leave you like a blank there. You just put the number. Count 1, 2, and 3. Easy. All right. But yeah, it'll look just like this. The quiz will look just like this. All right. Any other questions? More practice. All right. Practice makes perfect. Yes.
For D, it says 3H. But
Thank you very much. You the man. 6. That should be 6. Good eyes. That's successful. Right there. Excellent. So yeah, I see you're ready for 6. Thank you. All right. Let's do one more example. Anybody has another question? Paige, you're good? Awesome. Just messing with you. All right. This is an interesting one. And you'll see why in a minute. All right. So let's find the molecular formula. Let me go back here again. It's 126. So we're going to do this one. It's C6H15 N. C6H15N. C6H15N. All right. All right, here we go. I'm going to find the DUs. First thing I'll do. So this is 2 times 6 plus how many now? Plus 3, because we have a nitrogen. If we have a nitrogen, we add 3, remember? If we had 2 nitrogens, we'll have 4, we add 4. If we have 3 nitrogens, we add 5. All right. Plus 3 minus how many? 15. That's the number X. Divided by 2. It's equals to what? 2 times 6, 12. 12 plus 3 is 15. 15 minus 15 is 0. All right. 0 on saturations. Oh, good. All right. But then I only have 1, 2 types of carbons. Oh boy. And then I have 6 carbons on the formula. So I have a lot of mirroring here, symmetry. That means there's 4 carbons that are identical. Is that right? No, there's 6 carbons that are identical. So like it's pairing up. There's symmetry all over the place. Yeah, 3 and 3. So number 2, it says types. So we have 2 types of carbons. All right. All right. Number 3, we're going to solve for the infrared. All right. Okay. So check this out. I have a nitrogen. So I must have an amine, right? Or a imine. Those are the only 2 options. So let's see if it's an imine. An imine is a carbon with a double bond N. The 3000 line will solve for that. There's nothing on the left side, so there's not a double bond. There's also nothing here in this region for the double bond. So it's flat. So the only thing I see here is what? sp3CH. What about the fingerprint region? Does it tell me anything? No, doesn't tell me anything. That is just its fingerprint. It has 1, 2, 3, 4, 5, 6, 7. It has 7 peaks, but that's because that is inherited for that compound. All right, that's all I can assign. So I have an amine that is Tri-substituted. Exactly right. There's nothing here. If you had if it was mono-substituted, you would have 2 peaks. If it was di-substituted, you only have 1 peak here. But we don't have anything. So this is telling me that I have a nitrogen that has 3 connections. All right? Let's find out about those connections. They are here. Notice that also, I forgot to mention here. Let me go back over here. Another thing to do a quick check on we always need to do a quick check here. So notice that you count your protons integrations. Here will be 1, 2, that's 3, plus 1, that's 4, 4 plus 6, that's equal to 10 hydrogens. And that's exactly what I have here. All right? So we're going to do the same thing on this one. Let's go back to this one. We have 6 plus 9. It's equals to 15 hydrogens. That's what that integration is telling me. All right? All right. So the ratio is 6 to 9. If you had a ratio of 6 to 9 is equals to 2 to 3, you still need to figure that out. By, let's say this ratio would be like 2 to 3. Is it 2 to 3? Yeah. It's the same thing as 6 to 9. You just need to keep multiplying by a number. So, for example, I know that I have 15 hydrogens here. So if I multiply by 2, that makes it 4 and 6. That's still not enough. Then I have to multiply by 3. That makes it 6 and 9. You see that? That's how you would figure out based on the integration. All right? But I'm cool. I give you the actual numbers not to trip you. On an unknown, this is what you will get. You will get that number, the 3 and the 2. All right? So you just have to keep on multiplying by an integer so that you can get the right ratio, the full ratio. All right. I'm going to delete this. But this is all being recorded, so you can check it out. All right. So I have a quartet. Now the question is, what kind of group is this? If I said it was 2 to 3 to start, and then 4 to 6 and 6 to 9, what group is this of interest? It will be a CH2 that is repeating 3 times. You get it? That's tricky. But that's how that is. So you're going to have this signal repeating 3 times. We have symmetry all over the place. So the monomer, the one part that repeats, start with a CH2 and has how many neighbors? 3. Very good. Then we'll go to the next one. Also notice that this is around 1. This should raise a bell to you immediately. Ring a bell. And that's over here. So, oh, anything around 1, that has to be a CH3. You see? Piece all these things together. All right. So, what is this group then? This will be a CH3 that's repeating 3 times. And it's attached to what? To a CH2. All right? Because it's a triplet, so it has 2 neighbors. So 2 plus 1 is 3. All right, so we're going to solve for this. We're going to say, okay, this is a nitrogen that it's an amine that is 3 times substituted. This is called what? Triethylamine. So that will be the name. Let's put the name right here. Triethylamine. Very good. All right, let's solve. Oh, I forgot to do something else. I need to label the NMR, proton NMR. So this will be A, and this will be B. A, B. So that's all I have. I put A, and I put B here. And then I have what? So let's start with A. So what is A? A is a CH2 attached to a nitrogen. So that we haven't seen that yet. Where is that? Where is that? CH3, right here. Starts at a 2.2. All right. Let's do it. Let's do it. This is a 2.2 value. It's a CH2, so we have to add 0.3. No beta group yet. So that's equals to 2.5. Notice where this signal is right at 2.5. Perfect. We can predict that well. And it's a quartet that integrates to how many? 6. 6 hydrogens. All right. Let's do B now. B is what? Starts at 0.9, right? Because it's attached to a carbon. That signal is attached to a carbon. It's a CH3 attached to a carbon. I've seen it right there. So 0.9. Do we have a beta group? Yes. So here's the signal, alpha, beta. So we find something different than a hydrogen and an sp3 carbon. So that therefore is a beta group. That's going to be pulling the signal downfield. That's why we calculate these things, to calculate the shifts and see what's the electronic pull happening here. So this is approximately 1.2 ppms. We have about 1.0, which a little bit over 1, which is good. We're still within error. And this is a triplet that integrates for 9 hydrogens. All right. And we solve for this one. Oh, good. We have time. All right. Okay. Any other questions about this? All right. So the key thing here was to find out that we had a tertiary amine because of the nitrogen. And those 3 ethyl groups are equivalent. All right? All right. Let's do one more. Okie dokie. All right, unknown 63. This is the last one in the list here for the practice example packet. C8H8O. C8H8O. All right. Let's find the DU. First thing, find the DU. DU is equals to 2 times the number of carbons, that's 8, plus 2, because we don't have a nitrogen, minus the number of X, that's 8, divide all that by 2. That is equals to 2 times 8, 16, plus 2, that's 18. 18 minus 8 is 10. 10 divided by 2 is 5. So we have 5 unsaturations, of which 4 of them, every time you pass 4, or you have 4 and up, you're dealing with benzene rings. All right? So here you will have 1 benzene ring plus 1 more unsaturation. All right. Okie dokie. Okay, here we go. Okay, so next thing we do is find your types of carbons. It has how many types of carbons? So you have 1, 2, 3, 4, and notice that this insert says that it has 2. So there's 2 here. So 1, 2, 3, 4, 5, 6. We have 6 types of carbons. So that means there's 2 other ones that are, there's 4 carbons that are equivalent, 2 and 2. All right? So that's why I have only 6 unique types of carbons. This stumpy here is a triplet. That's the chloroform reference. Ignore that. This is what I told you about standard samples in the lab last Tuesday. Notice how clean these things are. Like there's very, very, very little impurities. You can almost like ignore that. The number of carbons is exact. The infrared, the proton NMR is really clean. There's not a lot of grass. And yeah, it looks good. All right, check this out. Notice that I'm giving you a number there for the carbonyl, 1707. Check out the formula. It has an oxygen. At 1707, what is that? We're going to solve the infrared as number 3. What is a signal of 1707? 1702. It's a carbonyl group. Very good. So far, what are your options for a carbonyl group based on your molecular structure? Aldehyde or ketone. Cancel carboxylic acid, cancel esters. Okay? All right. What is this thing here? That is an overtone. Very good. Ignore that. So if you take 1702, multiply that by 2, that is roughly right at 3404. And that's exactly what we have here. If we go like this, that's close to it. That's close to it. So this is an overtone. We're going to ignore that. Ignore that little blip. Awesome. So, next thing we'll do, we're going to trace a line for my 3000. All right? Do we have anything on the left side of that line? Any peaks? We should. We have a benzene ring. So this little thing right here, that's my benzene. Those are my sp2CHs. So this will be an sp2CH signal. It gets better. Let me see. Do we have sp3CHs? We have. Very, very small. These little blimps there, those little thingies. those are important signals. sp3CHs. All right, my favorite signal in the entire infrared world, the 2 horns. That's an aldehyde. That represents a CH stretch and a CH bend. That's why you get 2 horns. They're competing. So that's why you get 2 signals right there. And this represents your aldehyde group. So we know we have an aldehyde group. We can for sure assign that in the proton NMR. Now that, even though, you can actually see the CH of the aldehyde group in the proton NMR. And it's, all right, so that's 3. And then we're going to solve now for the proton NMR now. What is the next thing I'm going to do? Label these from A to Z. A. Let's do A, B, C here, just to be like cool. A, B, C, and D. All right? Okay. So what is that signal at 10? The what? The carbonyl doesn't show on the proton. But something you're on the right track. What is it? The CH from the aldehyde. Excellent. So this signal here at 10 is your carbonyl CH group, your aldehyde group. All right? And that's the signal in question. I'm going to block it. All right, B and C. Check this out. It's saying that it's integrating for 4. All of this is 4. So, what is that? Disubstituted benzene ring, because it only has 4 hydrogens. According to this pattern, are we dealing with an ortho, meta, or para? Para is the easiest one to spot. All right? The coolest of all of them, of course, is the meta, because it has a singlet, it has doublets, it has triplets, it has everything. And then you have the ortho. The ortho is a little more confusing. But the para is the easiest ones to spot. All right, so we have a benzene ring here that is that has 2 things. Let's put it like this. It has a X group and then a Y group. It's disubstituted. All right. And then we have D. What is D? CH3. This is a CH3. Very good. That is isolated with something that is blocking it from having any neighbors and no splittings. All right? All right. So we can solve this now. All right. So let's solve for this. We got everything. We got all the pieces together. We have a benzene ring that has an aldehyde marked as X, electron withdrawing group. Usually I put them as X, electron donating group, Y. Y, I don't know why, but it's a Y. CH3. All right. So we're good. Now we're going to label this structure with A, B, C, and D. This will be A. I know for certain this is D. The question is, where is B and where is C? Which one would be B? Closer to the electron withdrawing group. So that will be more downfield, more de-shielded. So that will be, this will be B, and this one will be also B. And this will be C and C. All right? Very good. So, I still haven't taught you how to name aldehydes, but I'm going to name it this one for you. All right. Unless you want to give it a try. What will be the name for that one? Any brave soul that dares to name this one? What if I tell you the ending is wait. What if I tell you that this root is benzaldehyde? 4-methyl benzaldehyde. Then the one is fine. Yeah. Yeah, that would be the name. Or you can say para-benzaldehyde. Yeah. But para-benzaldehyde is accepted. But whenever you use orthomet and para, that's actually been using, that's actually common naming. So systematic would be better to use 4. So I like systematic way. 4-methyl benzaldehyde. All right. because this whole thing is a root. All right, that's the root name. All right, let's do the labeling of the splittings here. All right, check out the chart. Here's the signal for the aldehyde. It's usually at 10. The carboxylic acid, it's between 10 and 12. I've seen it down to like 9.8 sometimes, up to 9.8. But you can tell by the infrared that, that will be a carboxylic acid. So that was easy. It still is easy to spot. But it's usually around 12, 11 to 12. All right. Check this out. So that's the aldehyde. So we'll say, okay, at 10, let me find a different pen. 10 ppms. That's a sharp value for my aldehyde. I have a singlet. And that is integrating to 1 hydrogen. Then B and C both are 7 to 8, by the way. There's both are in the same bracket. We'll just connecting the dots, making it separating the signals just to show that we dominate this thing. All right? Domination is the right word here. Total control, domination. All right, 7 to 8 ppm. That's also a chart value. In chart here. It's a doublet. B is not a beta group. Of the aldehyde?
Yeah. Because you have like an alpha aspartate carbon, and then the beta would be connected to the double bond.
That is a really good question. But since it's a bracket from 7 to 8, you already are including it. Yeah. Good question, though. I like that. Yes, sir. Question? Multiplet? Yeah. If it's mono-substituted, yes. Okay. Yeah. But since this is split and separated, you can see the two doublets. Okay. Very good. So this is doublet also. There's two doublets. This integrates for 2 hydrogen, and this one integrates for 2 hydrogens. All right. And then D is a CH3 where that signal starts. 2.3. Very good. Right there. That will be 2.3. And that's exactly what we see right here. 2.3. Look at that. That's about 2.2. Close. But yeah, 2.3 ppms chart. See, you can't be perfect in chemistry, but you can be close. Close to perfection. That means nothing, right? 2.3 ppm chart, singlet. My dad used to say, close, almost is nothing. Singlet integrates for 3 hydrogens, right? Yes, checking that out. All right, we're good. Any questions up to this point? Any last questions about proton NMR? Oh, I have something I want to share with you guys. When it comes to unique carbons, notice that all of these examples, there's no other ways for the molecule to rotate. And so pretty much these molecules are flat. Like if I have a plane of symmetry, I will put it right here between the carbonyl and the aldehyde to the methyl group. So the B's and the C's are mirror images, right? So that's easy to predict. But you might encounter, a matter of fact, you will encounter pretty soon, by next week, a case a case where you will have something like this. Let me see. Let me open this. We got a new section here. So what I'm trying to say here is when you have open chains, it's more difficult to spot the unique carbons, but you can still do it. Check out this example. One, two, three, four, five, six. What if I have this? How many unique carbons can you read there? 1, 2, 3. That's not right, but you're in the right track. Who say 5? My man there. How do you figure it out?
Split it down the middle, so the first one is on the BR, to the left is the second, to the left is the third, and then the 2 on the ends are 4 and 5.
Very good. So the other thing that I wanted to explain is, at first glance, it looks like 4. Right? You'll say, okay, this is equivalent to that. Let me get another pen color. You need this information for one of the unknown. So at first you say, okay, those are equivalent. And then you say 1, 2, 3, and 4, right? Because it's a mirror. But notice that what is called the chiral environment, because this molecule it's racemic, or if I give you a actual chiral, it's the same thing. You're still going to have 2 different environments for those methyl groups. Check this out. The environment from this methyl right here, with respect to this bromine, is kind of like cis. It's on the same side. And the environment for this CH3 right here, with respect to the bromine, is like if it was trans, across. You see that? That makes it unique. So in total, you have 5 types of carbons instead of 4. Don't let yourself get tripped in one of the unknowns that you'll have for the lab. All right? So you will have to count that like this. So it will be 1, 2, 3, 4, and then 5. You have 5 types of carbons here. And that's because those 2 methyl groups have different environments. They're not symmetrical.
So even though they can rotate because they're sigma bonds, it can still...
Yeah. Even though if they, and as a matter of fact, they're rotating like 1,000 miles an hour, like that, right? But there's still, at some point, one is up and one is down. One is up and one is down at some point in time. And therefore, that makes the carbon to have 5 types of carbons. Your carbon NMR will show 5 carbons instead of 4. So be careful. All right? Just a heads up. All right. Any other questions? Any other thing you want to learn? We haven't done much of the double bonds. So let's say we practice, let's practice one. Let's say we have this. So, okay, check this out. Double bonds are tricky because they, like, for example, if you have a double bond, like in this case, it is geminal, this proton will, so the signal for this proton, you count its neighbors, you add +1, but then this other one is going to take all of those signals and split it in half. So you're going to have more peaks. So that is an effect that the double bond does. All right, let me see. Okay, so let's do this. So let's label this A, B, C, and then this will be signal D and E. All right, so let's calculate here what this is. All right, so what is C? So let's see. So if we're going to calculate this, let's see. What is it? A, B, C, D, and E. All right. So if you have, let's do A. So what is A? A has one neighbor. So, but it will be split by its geminal hydrogen. So it'll be a doublet. And so the signals for the double bonds are right here. It's 5.5 to 6.5. So that will be, so we're going to do that. So these are kind of tricky. So this will be 5. So A will be a 5.5 to a 6.5. Plus it's a CH2, so it's 0.3, right? Yes. So this signal will be close between anything between 5.8 to 6.8, and it'll be a doublet of doublets. It'll look like 4 peaks. It'll have 4 peaks. So you will see that it looked like a quartet. But they will be at the same height. So A will be a doublet of doublets. So it'll be a signal that starts as a doublet, but then HB will split it in half. So it takes those two and splits it.
So it's like a similar process to W coupling?
It's kind of like the W coupling. Yes, it'll splits it. Mm-hmm. All right. B will be also similar, between 5.5 to 6.5. It'll have 0.3. I'm sorry, 0.3 extra because it's a CH2. It'll be anything between 5.8 to 6.8 ppms, and this one also will be a doublet of doublets, but check it out. Now, what the difference here will be is, like the signal from A to C, they will be more separated. So the J coupling will be wider, because A with respect to C is trans. B with respect to C is cis. So it starts as a doublet, but then HA splits it. And now it'll be, the J coupling will be smaller. And that's how you can identify, okay, you're going to say, this will be HA, this will be HB. You see what I'm saying? Because now it has a narrow J coupling. The J coupling is the distance between the two peaks multiplied by the NMR power. So it has a I don't remember off the top of my head, and I couldn't tell you. I would have to tell you, for example, the J coupling. See, for example, a J coupling of 14 versus one of like 6. This corresponds to a trans. This corresponds to a cis. You getting the point?
So a bigger number is trans.
Bigger number is trans, yes. And it's all related to the magnet. So I would have to give you the J coupling because I don't know the power of the magnet that proton NMR was run in. You see what I'm saying? It could be 300, 400 megahertz. It could be 900 megahertz. So I don't know. Kaylee, you had a question?
Yeah,
They will still integrate for 1. Yes, good question. So this will be integrate for 1 hydrogen, and this one will integrate for 1 hydrogen also. Yeah, and these ones are the multiplicities, so it'll look like that. All right, how about C?
Is there a range of values that we should know for terms in this? Like between 0 and 10 versus or something like that?
That's a good question. I've seen trends usually are above 10, and anything below 10 should be cis. You're welcome. How about C? What is C? Check this out. C will have how many neighbors? So C is still between 5.5 to 6.5. It's a CH, so you have to add 0.7. Notice that now you're adding the signals. So that will be equals to what? Anything between 6.2 to 7.2 ppms. And that will be what? That will be a quintet. Yeah, it has 4 neighbors. So it will be a quintet. So it will be a quintet that integrates for 1. And then you have D. D is what? D is attached to a, so this will be similar. So let's see. Oh, look at this. D will be this one. It started at 1.7. So it starts at 1.7 plus 0.3 because it's a CH2. It'll be it has 3 plus 1, that's 4 neighbors, that's also be a quintet that integrates for 2. And then lastly, we have E, that starts at 0.9 plus 0.3 because it has a beta group, right? That's equals to, this was equals to 2.0 ppm, and this will be equals to 1.2 ppm. It has a beta group on the double bond. You see that? Alpha, beta to it, to the left. And this will be also, this will be a quartet because it has 2 neighbors. I'm so sorry, it's triplet, thank you. It will be a triplet that integrates for 3 hydrogens. All right, we got 3 minutes. Any questions? All right, so double bonds are a little trickier. You can still do it. You can still do it. All right, have a wonderful day, guys. I'm going to stop the recording here. See you in lab. Take care.
Okay. A few questions for
Yeah.
you.
Let me see how I stop this. See you later, man. Give me 1 second. Why does it do that? Why does it do that? It hit the. Can I even stop it? It's right there. Give me 1 sec. I don't want to lose the recording. I hate when he does this. Oh, motherland. Let's see.
Yeah. I was just gonna ask.
Okay.